All right, so for this lesson, we're looking at dealing with quadratic functions in standard form, which is honestly, standard form of a quadratic function is when it's written something like this. We see in the right side here, this is in standard form. And when a quadratic function is written in standard form, the standard is we write the x squared first, and if there's a coefficient in front of it, in this case there's a 1, we call that we call that quite often the a coefficient. The coefficient of x we write second, and we call that the b coefficient, and the constant we write third. So when we write a quadratic function in this form, we call that it's written in standard form. And again, this, the standard way of describing the coefficients, the one of x squared is a, so ax squared plus bx plus c. So in this case, a is 1, b is 4, c is 10. And again, writing a quadratic expression in that form is really common when we're factoring and stuff we've done earlier. It's just not so useful for graphing. Whereas what we see right here is in vertex form. That's what we've seen in the last few lessons. Right? I can see the vertex. The vertex is at negative 2, 6. Hence, it's called vertex form. Well, these two equations are the same. And how can I show, the equations are different, but the function they represent is the same. And so how can I prove that? Well, one thing we could do is we could just graph both using technology. And you'll see you get the same parabola. However, what if you don't have Desmos or something? Well, the other option is to take one and put it into the other form algebraically. And right now, it's much easier for us to go from here to here than it is to go from here to here. We honestly haven't learned enough yet to take an equation in standard form, put it in vertex form. But we've definitely learned enough to take an equation in vertex form, put in standard form. So let me take my equation that I started with here in vertex form, x plus 2 all squared plus 6. And I can show quite quickly, using things we've done many times already in this course, really from previous courses, that this is equivalent to x squared plus 4x plus 10. And if I take this binomial that is squared, I can expand it really quickly, remembering it's going to be 3 terms. The first term is going to be x squared. The last term is going to be positive 4. The middle term is going to be x times 2 times 2, or x times positive 2 times 2, which is 4x. Plus 6, combine like terms, you can see I'm done. So again, this is standard form. This is vertex form. OK, now there's not a lot, like I said, that's actually useful about standard form for graphing. It's really useful for other things. But there's a bit we can do. And there is a way we can take an equation in standard form, perform a quick calculation, and figure out where the x coordinate of the vertex is. So again, right here I have an equation in vertex form, and the p there represents the coordinates of the x coordinate of the vertex. Right? If this equation had x minus 6 all squared, the vertex would have an x coordinate of positive 6. If the equation was x plus 6 all squared, the vertex would have an x coordinate of negative 6. And remember, in vertex form, we can see all those things really quickly. In standard form, it's something like this. It's ax squared plus bx plus c. So when I see an equation standard form, there is a way, again, I can see the x coordinate of that vertex, not as quickly as in vertex form, but with a quick calculation. So how is that? Well, I want to take this equation in vertex form and kind of put it into this form. How can I do that? Well, let's first kind of do what I did in the last question. Let's take this binomial squared and expand it. And so again, it's going to be 3 terms. The first term is x squared. The last term is positive p squared. And the middle term is x times negative p times 2. So negative 2xp plus q. And all of this is still times by a. So let me distribute the a. Got a lot of variables going on. I know. So I have ax squared minus 2. I'm going to write it as x. Actually, I'm going to put the a first. apx plus p squared. Oh, I think my letters mixed up. OK, what on earth was the point in this? OK, well, what I have here is actually quite similar to what we see here. For example, in standard form, a is what we usually use to denote the coefficient of x squared. Well, there's an a right there. B is what we usually use to denote the coefficient of x. That's all of this right here. All of this here we can think of as our coefficient of x, minus 2 times AP. and c is the constant, well, that's what we can call all of this over here. Oh, and there should be an a, sorry. I distributed the a here, but I forgot to write it in. There should be an a in front of the p squared. There we go. But still, everything you see highlighted in that pink is like my constant, and so that's like my c. And as well, if we look at the parts highlighted in green, that p right there is the x-coordinate of the vertex. So let's focus on this part, this minus 2ap, which is equivalent to our coefficient of x if we connect this back to here. Okay, I'm kind of connecting these things together. So let's formalize this. Let's write negative 2ap equals b. And again, remember that that p is the x-coordinate of the vertex. So let's divide both sides by negative 2a. And what do I have? I have the x-coordinate of the vertex must always be the same as b divided by negative 2a. Or the negative can just go anywhere. Negative b over 2a, same thing. And so if you have an equation in standard form, you know, this will show you the x-coordinate of the vertex. It's not as nice as just seeing the x-coordinate of the vertex in in vertex form, but it's not that much either. So for example, just to show you what this means, is b over minus 2a. If I go back to this first example here, I can tell by looking at the vertex form, the x-coordinate of the vertex is at negative 2. However, I can now fairly quickly find it out from here. If I know the x-coordinate of the vertex is going to be the same as minus the b value, the coefficient of x, 4, divided by 2 times the a value, which is 1. And I get negative 4 divided by 2, which is negative 2. And so, like I said, it's a relatively quick, actually it's a very quick calculation if you have an equation in standard form. But again, yeah, for graphing, vertex form is always going to be better. So let's kind of summarize really the last few lessons. So in vertex form, again, why did you go away? In vertex form, the a is the vertical stretch, and we talked about this already. Vertical stretch by a scale factor of a. As well, it can represent a vertical reflection if a is negative. And all that's mentioned in more detail in the previous lesson. This p, again, is affecting kind of shows us a horizontal translation. And in doing so, also shows us the x-coordinate of the vertex. In this case, it would be minus p. You know, the opposite sign is of whatever you have inside there. And lastly, the constant over here is the vertical translation. And as well, that tells us the y-coordinate of the vertex. In this case, it's just exactly the same as q. And again, nothing from here should be new. If anything here seems confusing, we should go back to previous lessons, because again, those are really, really important lessons. The new part was this, in standard form. Okay, and again, in standard form, the a we see here is the same thing as before. It's the exact same as above. Vertical stretch, scale factor of a, you can tell the reflection exact same. B, you know, that is not the x-coordinate of the vertex. That's just a coefficient of x. But I will say C is the y-intercept. Not the y-coordinate of the vertex, the y-intercept. However, if you want to find the x-coordinate of the vertex, like we mentioned before, it's not just, we can't just see it immediately from its standard form. We can calculate it by just going minus b divided by 2a. So again, it's not meaningless, but it's never going to be as helpful as vertex form for visualizing a graph. But it's a very pleasant way of showing a quadratic equation. Just all your different terms, biggest power to the constant. Very common way, especially when we're trying to factor things. So my final problem is really leading us into the next couple lessons, which is something I hinted about before, taking an equation in vertex form and, taking an equation in standard form and changing it to vertex form. So first, let's convert, like we've done before, x minus 4 all squared into standard form. So again, I can do this quite quickly. I can take this binomial squared, and I can quickly square this. First term will be x squared. Last term will be positive 16. The middle term will be x times negative 4 times 2 plus 6. Combine like terms. I have x squared minus 8x plus 22. There we go. Now it's in standard form. OK, but how can we go the other way around? How can I take this equation in vertex form, in standard form, and put it into vertex form? OK, so I have a different equation here now. So again, what we have here is in standard form. I want to put it into vertex form. How can I do that? Well, this is really the new part. So I'll show you here. But the process I'm about to go through is something called completing the square, which is really what the next couple lessons are about. So this is really kind of an intro to that. So the idea is this. If I look at this, this is not quite a perfect square. In fact, if I instead looked at x squared minus 6x plus 9, that is a perfect square. That there is exactly the same as x minus 3 times x minus 3. Now again, that's not what we started with, but it's close. I started with x squared minus 6x plus 10. This is x squared minus 6x plus 9. And so if this was what we're looking for, I could just factor it immediately because it's a perfect square, and I could see where my vertex was. Again, x minus 3 squared, that is a vertex that's been moved 3 to the right, and it hasn't been moved up and down at all. And if we want to put something in vertex form, we need to create a perfect square somehow. Because again, if you look in vertex form, it always has something squared. So always have to create a perfect square somehow, even though the function I gave you wasn't a perfect square. So now, again, what I have here is correct if that plus 10 was a plus 9. That said, I can easily now adjust that by just putting an extra little plus 1 right here. Right? 10, same as 9 plus 1. Which means if I kind of go back, if I just add a little plus 1 right here, now this must be in vertex form. And so I can now see this function x squared minus 6x plus 10 has a vertex 3 to the right and 1 up from the origin. Now, what I just did here, the process of going from here to here, that's called completing the square. And right now, honestly, all I'm hoping is that now that I've finished it, it kind of makes sense. You see that my sort of reasoning. What I started with was not a perfect square, so I found a perfect square that was close to it, and then it made everything balance out. However, to be honest, really, it's the next few lessons in which we go into this in great detail. So the more this makes sense, the better for the next few lessons. But really, it's just an intro, and that's where I'll stop.